For all the light in the cosmos, the most compelling mysteries are written in darkness, not an empty darkness, but a profound, gravitational darkness that bends the rules of reality itself. Welcome. This is a journey to the edge of understanding. Here are 100 facts about black holes and quantum spacetime. Fact 1. A black hole begins when the core of a massive, dying star collapses under its own gravity. Fact 2. This collapse can happen in less than a second, creating a supernova explosion that outshines an entire galaxy. Fact 3. What remains is crushed into a mathematical point of infinite density called a singularity. Fact 4. This singularity is wrapped by the event horizon, the point of no return where the escape velocity equals the speed of light. Fact 5. The size of a non-spinning black hole's event horizon is its Schwarzschild radius. Fact 6. To turn Earth into a black hole, you would need to compress all its mass into a sphere just 18 millimeters wide. Fact 7. Most black holes spin, described by the Kerr solution, which drags the fabric of spacetime around with it. Fact 8. This spinning creates a region outside the event horizon called the ergosphere, where nothing can remain stationary. Fact 9. Infalling matter forms a superheated, spinning structure called an accretion disk. Fact 10. Friction in this disk heats matter to millions of degrees, emitting powerful X-rays and making active black holes brilliant. Fact 11. Some black holes power relativistic jets, beams of plasma shot from their poles at nearly light speed. Fact 12. Stellar mass black holes, between 3 and 100 solar masses, form from the deaths of massive stars. Fact 13. Supermassive black holes, millions to billions of solar masses, reside at the center of most large galaxies. Fact 14. Our Milky Way galaxy orbits Sagittarius A*, a quiet supermassive black hole, 4 million times the Sun's mass. Fact 15. The missing link, intermediate mass black holes, are now being found through gravitational waves. Fact 16. The collision GW190521 created a 142 solar mass black hole, the first clear detection of an intermediate mass black hole. Fact 17. We find black holes by observing their gravitational influence on nearby stars and gas. Fact 18. The first strong black hole candidate, Cygnus X1, was discovered in 1971. Fact 19. The first direct image of a black hole's shadow was captured in 2019 by the Event Horizon Telescope. Fact 20. That image showed the supermassive black hole in galaxy M87, 55 million light-years away. Fact 21. Colliding black holes create the most powerful events in the universe since the Big Bang, rippling space-time with gravitational waves. Fact 22. The LIGO Observatory first detected these waves in 2015 from a merger over 1 billion light-years away. Fact 23. That detection measured a space-time distortion 1,000th the width of a proton. Fact 24. A black hole has only 3 defining properties: mass, spin, and electric charge, known as the no-hair theorem. Fact 25. This simplicity makes them perfect cosmic laboratories for testing the laws of physics. Fact 26. As you approach a black hole, tidal forces stretch you vertically and compress you horizontally in a process called spaghettification. Fact 27. To a distant observer, time for an infalling object appears to slow, freezing at the event horizon due to gravitational time dilation. Fact 28. The falling object's light would also redshift, becoming dimmer and redder until it fades from view. Fact 29. For the falling astronaut, crossing the event horizon is uneventful. There is no wall or sign. Fact 30. For large black holes, tidal forces at the event horizon are gentle enough that you could cross it without immediate harm. Fact 31. A black hole's gravity bends light, acting as a gravitational lens that distorts and magnifies background galaxies. Fact 32. Perfect alignment can create an Einstein ring, a complete circle of light around the black hole. Fact 33. This lensing effect allows astronomers to use black holes as natural telescopes to see further into the early universe. Fact 34. After a merger, the new black hole vibrates, or rings down, emitting gravitational waves that reveal its final mass and spin. Fact 35. Stephen Hawking theorized that black holes are not completely black, but emit a faint glow of radiation. Fact 36. This Hawking radiation arises from quantum fluctuations near the event horizon. Fact 37. Virtual particle pairs constantly popping into existence can be split, with one particle falling in and the other escaping. Fact 38. To an outside observer, this looks like the black hole is radiating and slowly losing mass. Fact 39. Therefore, black holes have a temperature inversely proportional to their mass. Fact 40. A solitary black hole will eventually evaporate over unimaginable timescales via this process. Fact 41. This evaporation creates the black hole information paradox, the greatest puzzle in theoretical physics. Fact 42. Hawking radiation appears random, carrying no information about what fell into the black hole. Fact 43. Quantum mechanics states that information is never destroyed. It must be preserved. Fact 44. If a black hole evaporates completely, the information about everything it consumed seems lost forever, violating quantum law. Fact 45. The debate over this paradox was known as the Black Hole Wars, with Hawking initially betting information was lost. Fact 46. The paradox suggests Einstein's theory of gravity and quantum mechanics are fundamentally incompatible at the event horizon. Fact 47. The leading solution is the holographic principle, proposed by Gerard Hooft and Leonard Susskind. Fact 48. It states all information within a 3D volume is encoded on its 2D boundary, like a hologram. Fact 49. For a black hole, all the data of what fell in is stored on the surface area of its event horizon. Fact 50. This implies the maximum information in any region of space is proportional to its surface area, not its volume. Fact 51. Our three-dimensional universe might be a projection of information stored on a distant two-dimensional surface. Fact 52. The firewall paradox proposes a searing wall of energy at the event horizon, destroying infalling objects to preserve information. Fact 53. This violates Einstein's principle that crossing the horizon should be uneventful, creating a major conflict in physics. Fact 54. String theory offers the fuzzball model, where black holes are tangled balls of strings with no sharp horizon. Fact 55. The ER equals EPR conjecture proposes a deep link between wormholes and quantum entanglement. Fact 56. ER stands for Einstein-Rosen bridges, the formal name for wormholes. Fact 57. EPR stands for Einstein, Podolsky-Rosen, referring to the paradox of quantum entanglement. Fact 58. ER equals EPR suggests two entangled particles are connected by a microscopic wormhole. Fact 59. This implies the fabric of space-time itself may be woven from a network of quantum entanglement. Fact 60. Some solutions to Einstein's equations suggest a black hole's interior could be a wormhole gateway to another universe. Fact 61. These wormholes, or Einstein-Rosen bridges, are likely unstable and would collapse instantly. Fact 62. To hold a wormhole open, you would need exotic matter with negative energy density. Fact 63. Theoretically, Certain wormhole geometries could allow for closed time-like curves, the basis for time travel paradoxes. Fact 64. Primordial black holes are a hypothetical class that could have formed from density fluctuations in the early universe. Fact 65. Some theories suggest these tiny, ancient black holes could constitute part of the universe's dark matter. Fact 66. Over timescales far exceeding the current age of the universe, even the largest black holes will evaporate via Hawking radiation. Fact 67. In its final second, an evaporating black hole would release energy equivalent to millions of megaton nuclear bombs. Fact 68. The largest structures in the universe, galaxy clusters, are often governed by central supermassive black holes. Fact 69. When galaxies merge, their central black holes eventually spiral together, a primary source of low-frequency gravitational waves. Fact 70. There is a maximum spin for a black hole, called the extremal limit, where the event horizon spins at the speed of light. Fact 71. The Penrose process describes how energy can theoretically be extracted from a spinning black hole. Fact 72. Matter can fall into the ergosphere, split, and one piece escape with more energy than it entered with. Fact 73. The most luminous, persistent objects in the cosmos are quasars, powered by supermassive black holes devouring matter. Fact 74. A single quasar can outshine its entire host galaxy from a region smaller than our solar system. Fact 75. The energy from a quasar's jets can heat galactic gas, shutting down star formation across an entire galaxy. Fact 76. The heaviest elements in the universe, like gold and platinum, are forged in the collisions of neutron stars and black holes. Fact 77. The gold in a wedding ring was likely created in such a cataclysmic merger billions of years ago. Fact 78. Evidence suggests Sagittarius A Times was an active quasar in the distant past. Fact 79. In the far future of a cold, dark universe, evaporating black holes may be the last significant sources of energy. Fact 80. Speculative theories like cosmological natural selection propose our universe was born inside a black hole in a parent universe. Fact 81. Inside a black hole, the roles of space and time swap. The radial direction toward the singularity becomes a future timeline. Fact 82. A black hole's entropy, or disorder, is proportional to the area of its event horizon, a key clue for the holographic principle. Fact 83. This entropy is enormous. A single stellar mass black hole holds more quantum information than all the particles in the visible universe.